Hello, everyone. Um, Today, we would like to talk about discrete Fourier transforms, and we will start from absolute first principles. Okay, so let's get going. Consider a signal as follows. Let's say this is your voice saying hello, and the signal looks like that. Let's say you digitally sample this signal at time, let's say t0, t1, t2, all the way till tn minus 1. And let's say your samples look like this. And let's call these samples x0, x1, x2, x3, and so on till xn minus 1. Now, if we only have the digital samples, then it's equivalent to just deleting this. Now, often this signal x0, x1, x2 is written as a vector x, and the vector x is essentially this array of numbers or a vector x0, x1, x2 till xn minus 1. Now, when you think of a vector, you always express that vector in a vector space. So we also commonly express this vector x, and the question is, in what space are we expressing this vector? Okay. Turns out that we can express this vector in the time space where this is time, and the dimensions of the dimensions of time would be t0, t1, t2, so on till tn minus 1. So this is essentially an n-dimensional space, Rn, and x is a vector in that n-dimensional space. And each of these dimensions of time can now be written as a vector themselves, such as t0 can be written as 1, 0, 0, 0, 0, 0. T1 can be written as 0, 1, 0, 0, 0. And all the way tn minus 1 can be written as 0, 0, 0 till, and the last one being 1. In other words, this vector t0 corresponds to this time. This vector t1 corresponds to this time. And finally, this vector tn minus 1 corresponds to this time. So one can then think of x as when it's projected to different dimensions, like x's projection on time t0 is nothing but x0, which is exactly this value. X's projection on time t2, on time t1 is this value x1, and we can keep going. Right? So then x can be written as nothing but the projection x0 times the vector t0 plus the projection x1 times the vector on which it's projected, which is 0, 1, 0, 0, all the way to vector xn minus 1 times 0, 0, 0, dot, 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 till 1. Right? This is very simple. All we are doing is taking the vector's projection on each of the different dimensions, and we are writing out x as a sum of the weighted sum of each of these dimensions. Which means now we can write x as 1, 0, 0, 0, so on, 0, 1, 0, 0, 0, so on, all the way till 0, 0, 0, 1 times x0, x1, so on till xn minus 1. Okay. As you've already identified, this is the identity matrix, but it's also the basis vectors. So this basis vector is also called the time basis. And of course, the signal is being expressed. The signal is x0, x1, x2, all the way till xn minus 1. This signal is being expressed in the time domain or in the time basis. Now look, let's first copy all this basis and the signal and paste it here. Remember, this is our signal x. I could express the same signal x, maybe in a different basis, by perhaps changing this basis or rotating this basis. And as I rotate these basis vectors, the value of x, the vector x, is going to change. So my question is, my point is, time is not anything special. We could potentially express the same vector x in other bases, in the same n-dimensional space, but with other basis vectors. And once we do that, let's call this new basis, for the lack of a better name, let's call them f0, f1, f2, dot, 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 fn minus 1. Okay. Obviously, actually, let's move this whole thing a little bit so we have some space. Obviously, the values of x is now going to be different, because now we will project x onto f0, and let's call that value z0. Earlier in the time dimension, it was x0. Once we project onto f1, we have the value z1, all the way till fn minus 1, we have value zn minus 1. Right? So now x is a new vector, although it's the same signal, but it's expressed as a new vector where that vector is z0, z1, z2 till zn minus 1. Okay? And similarly, if we now express this signal x in this new basis, then we will write this in the following way. X vector is in this new basis where the columns of the basis are f0, f1, all the way till fn minus 1 times z0, z1, z2, all the way till zn minus 1. Which means, observe that I can write both of these x's, which are the same. I can now write this equation, ix equals f xz. Let's call them xx and xz. So, or let's call them ix in the time domain and fx in the f domain. Fourier showed that there is such an F matrix which gives you such F0, F1 all the way till Fn minus 1 basis vectors. And once you express the same signal in this basis vector, there's good amount of meaning that you can extract from the signal. And then the corresponding values of Z0, Z1 all the way till Zn minus 1, this is nothing but the Fourier transform of the signal X. Let's now look at how we can derive the Fourier transform once we look at Fourier transforms as nothing but a change of basis from the time domain basis to the frequency domain basis. Okay. So our goal now is to understand what is this matrix F, which is essentially a basis set of basis vectors for the n-dimensional space. And to do that, we need to go to first principles, and we need to start thinking about this through rotations. Okay, so let me motivate what it means. So imagine a stick. This is a stick of length 1 that is rotating. The stick is spinning. Okay. Now if I want to model this rotating stick mathematically, then one way of modeling it is saying that I want to understand the location of the endpoint of the stick at different times. Right? If I can express the location of the stick at different times, then I have been able to model rotations. Right? Now, one way to express the location of the stick is the following. At time t0, the location of the stick is 1. At time t1, you can think of the location of the stick as, well, if this is theta, then cos theta plus, this is not only cos theta, there's also the location of the stick is also has some component in the vertical direction. So, and that vertical direction component is sine theta. So I can express the stick as cos theta plus some sine theta in the perpendicular direction. So when I use this symbol, what I mean is this is in the perpendicular direction of the direction of cos theta. Makes sense. Now at time t2, let's say the stick is moving with a uniform speed, with an uniform angular speed. So then at time t2, this should be cos 2 theta plus in the perpendicular direction sine 2 theta. All the way till Tn minus 1, where it should be cos n minus 1 theta plus perpendicular direction sine n minus 1 theta, which is this one. And this is n minus 1 theta. Let's say we want to express in n samples one full rotation of the stick, and therefore theta is nothing but 2 pi by n. Okay, great. Actually, let's make this capital N for now, because that is the maximum, the total n samples we are going to use. So this one also is capital N. Wonderful. But this is still not math because we have this weird symbol of perpendicular and we don't know how to manage that. Right? So humans just made up a symbol, let's call it J, that would denote a rotation of 90 degrees so that we can express this same value cos theta plus perpendicular sine theta as nothing but cos theta plus j sine theta. Right? This would be 1 plus j 0. This would be similarly cos 2 theta plus j sine 2 theta. You might be saying, hey, how can you make up such things in mathematics? You're just arbitrarily coming up with a symbol j. I would argue with you, we've always made up such symbols. For instance, when you think of numbers, you think of positive numbers going in the right side on the right hand direction, and those numbers are 1, 2, 3, 4 all the way, keeps increasing. But then we wanted to create numbers that are negative. We thought, oh, let's invent this notion of negative numbers. That was completely imaginary. There is no such thing as -5 boxes. So we just made up the notion of negative numbers, and we said we are going to represent negative numbers with a arrow on the leftward side, and we are going to call these numbers with a dash sign before it. So if we say -1, it means the opposite of 1. We made it up completely as a matter of imagination. Right? So if you're happy to accept such figments of imagination, I would submit that you should not have any problems now to accept that I'm now going to create another line in the vertical direction, which is a 90-degree rotation, and I'm going to express any vector as something along my horizontal axis plus j of the vertical axis, where j corresponds to a 90-degree rotation. Okay. But then you have to say, okay, look, if I now take a stick along the horizontal axis of value 1, if I give it a rotation j, then the stick becomes j. What if I give that rotated stick one more rotation? So j times, or j of j, the operation j on top of the rotated stick j is j square. And that means that I take a stick like this, which is 1, I make it j, the vertical stick is j, and now I make another rotation on j, which becomes this, and I know that that stick is nothing but -1 because I already defined this notion of negative, which means j is square root of -1. I don't know how to calculate that number, therefore I call it a complex number. But the good part is, like negative numbers, when you deal with real things, you model negative numbers, but eventually in real applications, the negative numbers go away, and then you realize that the answer is still a positive number. Similarly, in many of these cases, when we deal with real signals, we will see that although we have this imagination of square root of -1, they will cancel out in the right ways, and we're left with something that is physically possible, that is feasible. Okay, great. So then we have this situation where we are expressing the location of the stick in terms of cos n-1 theta, the last location, plus j sine n-1 theta. And then remember, from Euler's equation, this turns out to be equal to e to the power j theta. This becomes e to the power j2 theta. this becomes e to the power j0 and all the way till e to the power j n minus 1 theta. In other words, what I have said is the spinning stick can essentially be expressed as a vector where the vector is nothing but e to the power j0, which corresponds to this location of the stick, then e to the power j theta, which corresponds to the next location, e to the power j2 theta, and so on till e to the power j n minus 1 theta. This vector is nothing but a spinning stick which is spinning at the frequency of 1 cycle per n time units. Right? Okay. Now I ask you the next question. Hey, what if the stick starts spinning at double the speed? Can I now model the rotation of the stick? It's not too hard. Why? Because all I need to do is the following. I can say e to the power j0, which is still the starting position of the stick. But what is the next position of the stick going to be? Well, the stick is rotating at twice the speed. So the next position is going to be 2 theta. The next position is going to be 4 theta, and so on. So then I can express that stick as e to the power j0, e to the power j2 theta, e to the power j4 theta, so on, e to the power j twice of n minus 1 theta. This is a frequency. Let's call this initial frequency f1. This frequency is f2, which is 2 cycles per n time steps. Agreed? Very good. I can keep going. And if I want n such frequencies, which means I'll start with frequency 0. Actually, let's talk about frequency 0 quickly. If the stick is rotating with 0 frequency or 0 speed, that means the stick is not moving from its original position. So we can write frequency f0 in which the stick is not moving at all. F0 is nothing but 0 cycles per n times. Then I can express the stick as e to the power j0, e to the power j0, e to the power j0, all the way till e to the power j0, because the stick is static. And that's what we call as f0, 0 cycles per n time units. Okay. But now let's go all the way to n minus 1, because we want n frequencies, right? Like we had n time, remember? We had n different time vectors, here, 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 all the way till tn minus 1. So similarly, we want n different frequency vectors. So let's go all the way higher. So if we go all the way here, then we want fn minus 1. And that is basically n minus 1 cycles per n times, time units. And what would that vector look like? Well, that vector, the starting point is still e to the power j0. But what's the second point? Once it starts, what's the next one? Observe that once this is the faster spinning vector, this is spinning very fast, n minus 1 times the frequency f1. So n minus 1 times means in the first step, it's going to go to n minus 1 theta. In the second step, it's going to go to 2 times n minus 1 theta. Third step, it's going to go to 3 times n minus 1 theta, right? So then we can write that as e to the power j0, e to the power j n minus 1 theta, e to the power j 2 times n minus 1 theta, all the way e to the power j n minus 1 times n minus 1, which is n minus 1 square theta. And that vector represent the fastest spinning stick, where the spinning frequency is n times this spinning frequency. Very good. Fourier, very interestingly, made the observation that these frequency vectors that we can call f0, f1, f2, all the way till fn minus 1. Fourier said, you take any of these two vectors, they will be orthogonal. Again, you take any of these two pair of vectors, you take f1 and f2, and you do a dot product, it will be 0. You take f2 and fn minus 1, you do a dot product, it's going to be 0. Which means these vectors together, they can represent an n-dimensional space. And not only that, they are an orthogonal basis for the n-dimensional space. Okay. So then I can now express, remember we can bring back I xt equals f xz, right? So then I can now write this as I as 1, 1, 1, 1, 0, 0, 0, 0, 0, 0 times x equals this F matrix, which is nothing but the F matrix is now this matrix. The columns of the F matrix are each of these individual columns. So I can write that as F0, which is this column, then F1, F2, Fn minus 1 times Z0, Z1, Z2, Cn minus 1. Okay. This is called the Fourier transform. So what is Fourier transform saying? It's saying something very interesting. It's saying that if you give me any signal, x0, x1, x2, I can compose that signal by adding up a bunch of rotations and multiplying each of these rotations with some coefficients. In other words, any signal is essentially a sum of cos and sine sinusoids, right? Because remember, e to the power j0 or e to the power j theta is nothing but cos plus j sine theta. So which means I can make, it's like these vectors are like Lego blocks. You give me any structure, I can make up that structure by combining these Lego blocks, by putting them together. So similarly, Fourier transform is saying, you give me any signal, I will make that signal by combining these Lego blocks. But of course, I might multiply each of these Lego blocks with bigger numbers or smaller numbers, make them big or small to really match it. But I can always make up any of these signals with these sinusoidal Lego blocks, and that is beautiful, right? I can always break a signal into these small sinusoidal Lego blocks. Of course, these Lego blocks will have different sizes based on how large these coefficients Z0, Z1, Z2 are. Okay, so now let's quickly write this mathematically to express Fourier transform in a mathematical equation. We can write this as Fz equals x. Therefore, z is F inverse of x. Now, because F is an orthonormal matrix, we can always normalize this matrix by multiplying them by 1 by square root n. Right? A matrix is orthogonal. You can always orthonormalize it by just divide it by the length of the vectors. And all the vectors f0, f1 of the same length, so you can divide it by 1 by square root of n. And that means z, which is a vector, is nothing but F inverse x, and an orthonormal matrix's inverse is nothing but F conjugate transpose times x, which means we have F0 conjugate, F1 conjugate, so on till Fn minus 1 conjugate times x0, x1, xn minus 1. Right? That is nothing but this z0, z1, z2, zn minus 1. Very good. So then what should the equation be? Let's take z2. So z2 should be e to the power minus j0 times x0. That's the first value of f2, plus e to the power minus j 2 theta times x1, plus e to the power minus j 2 times 2 theta, which is 4 theta, times x2, all the way till e to the power minus j n minus 1 2 theta times x of n minus 1. Actually, I should be careful. I think I made a slight mistake. All of these small n's should actually be capital N, right? Because that's the maximum. Capital N is the maximum number of samples of time or frequency that you're taking. Great. And that should be the case in the above equations too, where these all should be capital N. Sorry for that. Great. Okay. Great. So then we can write this equation more generally, which is Z2 is nothing but sum. X is actually increasing. So let's write that X as N. And this N goes from 0 to N minus 1. Now you see why I had to make the lowercase n uppercase. So x0 is going, x is going from 0 to capital N minus 1 multiplied by e to the power minus j 2 theta, which tells me the speed, because z2, remember, was the second speed. So that goes increments by 2 theta times, it keeps, here there is an n because 2 theta, twice 2 theta, 3 times 2 theta, so on till n minus 1 2 theta, right? And this is where theta is nothing but 2 pi by n. Right? Great. We're almost there. So now if we want to write generally what is Zm, where m corresponds to the mth frequency, then we can write that as sigma n equals 0 to n minus 1 xn times e to the power minus j. Now look, because this is m, this should be m theta, and theta is 2 pi by n. So m times 2 pi by n times n. And I'm going to just reorder them and write it cleanly as minus j 2 pi by n times mn. Okay. I need to do one more small thing. Remember, this was a orthonormal matrix. We want that to be an orthonormal matrix. So every column of F, we want to normalize it by the length, and the length of that is 1 by square root n. So I'm going to normalize that by 1 by square root n to make it orthonormal. Lo and behold, this is the equation of discrete Fourier transform. Maybe the equation is not the most important thing here. The thing to understand is that the coefficients in the frequency domain are actually the signal x projected to each of the frequency basis vectors. That's the beauty of Fourier transform. And now we can easily write the other way, which is the inverse Fourier transform. That's inverse DFT, which says I know the Fourier transform. How can I get x? Means I convert from the frequency domain back to the time domain. And that would essentially mean I want x equals f times z. I want to know x. Remember, x is nothing but x0, x1, blah, blah, blah. And z is nothing but z0, z1, blah, blah, blah. So I want to x. So observe that if you want the general value of xn, that would be nothing but sigma. Now it's going to go from m equals 0 to n minus 1, where m is the frequency. And you would do zm times e to the power. And now it's no longer minus j, because remember, you don't have to do an inverse anymore. So this is e to the power j 2 pi by n times nm, 1 by square root n. And this gives you the equation of the inverse Fourier transform. So now you have a way to go from time domain to frequency domain, because Zm are the coefficients in frequency domain. And if you know the frequency domain signal, Zm, you have a way to go back to the time domain. And all you're doing is you're expressing the same signal in different basis vectors. Okay? As a very quick analogy, this is oftentimes my young students get excited, is that imagine the signal that you care about is a pizza. Let's say it's a pizza. And you can cook pizza in one basis, which is maybe flour, cheese, and salt, or yeah, let's say salt. But you can cook the same pizza in a different basis, which might be bread, milk, and what is another salty kind of a pepper, right? So if you think about it, the amount of ingredients that you will need, the amount of flour that you would need, let's call that x0, The amount of cheese that you will need, let's call that x1. The amount of salt that you need, let's call that x2. The pizza in this domain is essentially x0, x1, x2, where x0 represents the amount of flour you need. Whereas pizza in this other domain, which is z0, z1, z2, corresponds to the amount of bread, which is z0, the amount of milk, which is z1, the amount of pepper, which is z2. That's the amounts that you need in this other basis. Nonetheless, both of them are pizzas. Okay, so I hope this gives you a view of what Fourier transforms really means, and at the same time gives you a mathematical appreciation of how you express that. But the core fundamental of it actually goes back to nothing but looking at the same signal from different angles. And in this case, angles means different basis vectors. So often people ask me, why do I care? Why do I want to change the basis? Well, there could be many reasons. I'll just quickly give you one example. Let's say your car is making a weird noise and you don't know what is going on. And you look at the signal of the sound, and the sound looks like a normal signal. You do not know why the car is making that noise. So what you could do is you could take the Fourier transform of the car's noise, right? And then you could look at all the frequencies that make up that sound signal that you're hearing. And maybe you will see that among all the frequencies, there is one frequency that is pretty loud. And if you know, maybe the car's piston oscillates at a certain frequency, and you see, oh, look, the car's piston frequency matches with this large frequency that I'm seeing in the car's noise, then you can debug that, maybe this car's noise is coming from the fact that something's wrong with the piston, because seems like the piston's frequency matches with the dominant frequency in the car's noise, and that helps you debug signals. Okay, that's just one example why looking at a signal in a different angle from a different perspective, a different basis, gives you interesting insights into the signal. And Fourier transform is great in giving you this other view of signals and has tremendous amount of applications. Okay, great.